Okay, welcome everybody. So we are today for one more of our Munich AI colloquium talks. Today we have a speaker that is Stéphane Mallat, and I would like first to introduce him. So Stéphane is an applied mathematician, and he's actually having also a degree in electrical engineering. And he's currently professor at the Collège de France, but also at the École Normale. And he has a chair in data science. He is a member of the French Academy of Sciences, the Academy of Technologies, and a foreign member of the US National Academy of Engineering. He has spent several years in the US. For a decade, he was professor at the Courant Institute of New York. And later on, he took chairs at the École Polytechnique and the École Normale Supérieure in Paris. Stéphane's main interest has been for long harmonic analysis, the way to apply that, to make it computational, to perform signal processing, and also in the area of machine learning, he has brought groundbreaking contributions. He developed, and one of these masterpieces in the area of computational harmonic analysis was the so-called multi-resolution analysis, which is a theory that is able to explain how wavelets can get constructed and how these could determine a computational tool for signal processing. And he has been working for many years also on the usage of these tools for image processing and also sparse representations of signals. In the past years, he has been interested in understanding deep neural networks and their mysteries. And in particular, he has been developing the so-called scattering transform that brings together the power of wavelet theory with the challenge of the nonlinearity that is typical for deep neural networks, to explain how certain representations of images can become somehow invariant with respect to certain deformations. So today he's presenting for us some mathematical mysteries of deep neural networks. And I would like now to ask everybody that have the video on, maybe to turn it off, so that we have maximal bandwidth and stability for his talk. So thanks, Stéphane, for being with us, and I let you start now your talk. Thank you very much.
Thank you, Massimo, for this invitation and warm welcoming. So yes, I'll be speaking today about these mathematical mysteries of deep neural networks. There is now a whole community of mathematicians trying to understand the performance of these deep networks from different point of view: harmonic analysis, optimization, probability. And the point of view I'll be taking today is also a mix of all these different aspects. So the problems that are concerned are the general problems of high-dimensional learning. So there is really two sides, as you know, to high-dimensional learning. There are the unsupervised problems, which is really about building models of the probability distribution P of X of the data from a certain number of samples. So I'll be very much in this talk inspired by statistical physics. And in statistical physics at equilibrium, you can describe a system through its probability distribution, which is going to be defined by a Gibbs energy. So the probability distribution has this kind of exponential form, and that allows to explain many different systems, from cosmology here, observation of matter density, to turbulences examples. And then you have the other side, which is supervised learning, where you're really interested in estimating a class or a certain parameter y, which, for example, in physics would be, for example, an energy, given examples. And I'll be today trying to look at both point of views and their relations. Now, the central topic is, of course, the performance of these deep neural networks that you all know pretty well. So let me just remind the architectures of these networks. You take an input, your data in high dimension, here it's an image, and then you apply convolution operators of a relatively small support and a nonlinearity, which is here a rectifier. And all these filters are going to define the next layer, which potentially will be subsampled images. And then essentially you repeat the same thing. In other words, you apply filters to each of these images, sum the output, you're going to get a result after applying your rectifier. And for all different filters, you'll get different channels of the next layer, which you are going to cascade until essentially the spatial dimension has nearly disappeared. And you now have a representation out of which, through a linear combination, you get your estimator. So in this network, the parameters are all these huge convolutional operators. This is the overall parameters of the network that you essentially want to optimize in order to minimize some loss, for example, of classifications on the training data. And as you know, in about 2010-12, there were absolutely exceptional results that have been obtained. First for image classification, then for speech, sounds, now very spectacular results on languages, but also regression in physics, signal and image generations, and so on. So obviously, there are very fundamental questions on why can we capture such diverse phenomena with such generic architecture. So there are different kinds of questions. First of all, the optimization, of course. How come a simple gradient descent or stochastic gradient descent would lead to reasonable solutions? But also there are questions about the architecture, which is very particular. You have a succession of convolution and subsampling. So why such convolutions? Can we interpret the mathematical models of this last layer, which gives the solution through a final linear estimators? Obviously, there is a kind of scale parameters that goes across the layer, because each time you use small filters, but you subsample. So at the deepest layer, you basically progressively aggregate the information at each scale. There are these nonlinearities, which have very important role that we need to understand. And all this is leading us to a mixture of different areas of mathematics, obviously probabilities and statistics, but also harmonic analysis and optimization. Harmonic analysis, you can see it by looking just at the filters of the first layer. They look like small wave, which I'll call here wavelets. So something of the domain of harmonic analysis is clearly happening here. And we see also this cascade of convolutions, which leads to think in harmonic analysis terms. So the overview of the talk will be to try to put together these 3 points of view and raise questions. I'm not going here to begin from the architecture. I'm rather going to begin from problems in physics, where we do need to learn high dimensional probability distribution from priors and try to understand from first principles what kind of regularities do we have in order to build such models. And scale will come as a very natural tool. There is a lot of work that has been done around the renormalization group that I'll be briefly summarized to show how such structure at different layers naturally appears. Then the second part of the talk, I'll move towards more deep network-like architecture. But first of all, I'll try to almost eliminate the learning and show that one key issue in these problems is really not so much to separate scale, but to understand interactions across scale. And at one point, learning is absolutely needed to do so. And I'll try to discuss the role of learning and open questions around that. So that will be the overview. So let me begin from the point of view of physics. So what would it mean to learn physics given samples of physical field? It essentially means to try to learn the energy of the systems, which defines the probability distributions of these different images or physical fields. That means we need to come out with models, indexed here by a parameter theta, and identify the appropriate parameter. So once you have a model, to identify the appropriate parameter theta is not so difficult. In statistical term, you can define maximum likelihood estimation, which essentially will amount to minimize a loss over the observation, which is the sum of the log probability of the different observation. So you can try to do such, and that's typically the kind of loss that are used in neural nets, which you can try to minimize with a gradient descent. So immediately you have optimization question which comes, will the gradient descent converge and how fast will it converge? But really the difficult questions are not so much there. The difficult question is to come out with an appropriate models for complex physical fields. What kind of prior will allow us to define such models? So the first kind of idea that comes to mind if you are doing math or physics is to use prior information about the symmetries of your probability distribution. If the probability distribution is invariant, let's say, to translation, to rotation, or to small deformation, to certain diffeomorphism, then you can use it, take advantage of this prior information to try to define these models. And that's a line of work that has been followed by a number of researchers, including myself. But I'd like to argue that this is not enough. It doesn't bring enough information, and we need to find other source of regularities to define such probability distribution. So before doing so, let me just quickly glance on the optimization problem. The optimization will consist in doing a gradient descent on the parameters in order to minimize the loss. So obviously the gradient descent is going to be governed by the Hessian of the loss. And there is this very basic optimization theorems, which basically says that if the Hessian is well conditioned, is in between the minimum and the maximum eigenvalues are positive and have a ratio which is not too large, then the gradient descent has exponential convergence. You have a convex problem. Now, this is obviously not going to be the case very often, but it will be the case if you use a linear model. In other words, if the energy is related to the parameter by a linear form through, let's say, the last layer, if you think of it, of your network, if you know it, then you can show that the Hessian is positive. The only problem is potentially it's not going to be stable. Okay, now back to the model. What kind of regularity can we use? What I'd like to argue here is that a very strong source of regularity is the regularity of these high-dimensional data across scale, and that's really rooted in the work of the renormalization group of Kadanoff first and Wilson in the 70s. So the idea is the following. If you take a field like that, an image, X, if you try to coarsen this image at different scale by just averaging and subsampling, you are going to get images of progressively smaller size. What you can try to do is to look at the probability distribution of these images at these different scales. And one observation is that the evolution of this probability distribution is usually very regular. What does that mean? It means that if you can find a parameterization of this probability distribution, these parameters are going to have a very smooth evolution across scale. Now, what Wilson showed is, in fact, when you have a physical phenomena at phase transition, let's say when you go from liquid to gas, then you reach a self-similar stage where, in fact, all these probability distributions are identical. In other words, under appropriate renormalization, your parameters will all be the same. Okay, but of course, we're not usually not in that kind of situation. But what this intuition is telling us is that what is going to be important is to understand how we move from one scale to the other. And in other words, what is the conditional probability of the fine scale given the coarser scale? Now, if you apply this idea that you can move progressively from coarse to fine, and you'll get a kind of Markov chain which progressively will lead to the probability of the very fine scale as a product of these conditional probabilities along this chain. So the question is to model these conditional probabilities. The key idea of Wilson is to say, okay, this information at coarse scale is included into the fine scale. So what you would like to do is to decompose the fine scale into the coarse scale and some orthogonal coordinates, which basically gives the high frequency information included here. And the first idea is to do that in Fourier, but we'll see other alternatives. And if you can do that, then the conditional probability of the fine scale given the coarse scale is the same than getting these unknown degrees of freedom at high frequencies. So how to represent these degrees of freedom? So what we need is to decompose the fine scale into coarser scale and some high frequencies. And that's where wavelets will come. Wavelets come in naturally here because you have the group of translation and rotations which are built in the wavelet and which play a very important role in this probability distribution. So what is a wavelet? It's a local waveform, which is going to be dilated at different scale and translated at interval 2 to the j. Now, if you design well your wavelets, you can get an orthogonal basis of your space. Now, what's the relation with our problem? The way you compute a fast wavelet transform is you get the fine scale information, you decompose it into a coarse scale with a filter and a subsampling, and the wavelet coefficients are obtained with 3 other filters and subsampling. And if you look at them, they look almost like a white noise in this case. And as I said, the conditional probabilities will be given, in fact, by knowing the probability of these high frequencies given the low frequency. Now, of course, you can cascade that and do that at each scale. So the point of view that it gives, and this is the joint work with Thierry Marchand, Misaki Ozawa, and Giulio Biroli, who are physicists, the idea is that now you are essentially factorizing your probability distribution as the very coarse scale, which is after large averaging will be essentially Gaussian, and the probabilities of each of these high frequency wavelet coefficients given the low frequency. Now, the models that I'm going to show you can build is not on the original probability distribution, but it's on these conditional probability distribution. And what is going to be very important is to renormalize these wavelet coefficients so that their variance remains always of the order of 1. Suppose you can compute these models. Then you can sample your field with a coarse to fine strategy. You first begin at your very coarse scale. Now you synthesize the high frequencies given the low frequency with the conditional probability distribution, which allows you to get the next scale. You synthesize high frequencies and you reconstruct the next scale. With your model, you synthesize again the wavelet coefficient given the coarse scale, and so on. So the central claim here is twofold. First of all, we are going to can build such model with relatively simple linear model, even for complex ergodic physical fields. The second claim is that the renormalization, which is in the renormalization group, is in fact performing a conditioning of the Haitian and that leads to fast convergence of the gradient descent. And that has very close relation. In fact, it's completely rooted into the whole program in harmonic analysis of building equivalences between norm. That can be shown on Gaussian processes, but I will skip that in interest of time. Let me show example. I'm first going to begin with the most classical models in statistical physics, which is the continuous version of Ising called phi-4. Basically, it's a field whose values are always close to -1 and 1 because of a potential. The energy has a cinetic term like a Gaussian process, which is specified by a Laplacian. So you can define that as a linear model. But if you arrive close to a critical temperature, you have very long-range correlation phenomena which appears. And if you try to sample or identify the parameters of such a model, it gets extremely slow to converge when you are close to the critical temperature. If you factorize this model in wavelet domain, then all the parameters converge very quickly because essentially the conditional probability are preconditioning these kind of energies. Now, suppose you don't have the model. This is the case of weak lensing. So this is a problem in cosmology. You have a new satellite being sent for that, where you visualize galaxies. And because of the light deformation of the galaxies, you can infer the distribution of black matter because of the lensing effect produced by gravity. So an important problem is to define the statistical distribution of that kind of field. Now, if you use the kind of linear model in wavelet orthogonal basis given by these conditional probabilities, you can build accurate models, and these models are being sampled here. Here you have synthesis of such example. Now, what are we doing here? We're essentially using an incredibly simple neural network where there is only one layer at each scale, and the interaction across scale is given by these models, which is specified by the potential, which requires using ReLU to approximate it, and covariance moments. Okay, but that's too simple. It's not going to work for something as complex, let's say, as turbulence. So what are we missing? If you look at a wavelet transform of, let's say, boats, structured images like that, at different scale, what you see is that, okay, the images are very sparse. Most coefficients are zeros besides the edges. But more important, they are extremely correlated or dependent across scale. And what is going to be very important is to be able to capture this dependence across scale. In other words, capture the dependence with more sophisticated model of fine scale given coarse scale, which is equivalent to capture the dependence of the wavelet coefficient, where you see these alignments of edges. And that comes to the problems of these scale interactions and the core problems of learning. So the problem now in this conditional renormalization framework with wavelet is to specify these conditional probabilities. In other words, the dependence of the high frequency wavelets given the low frequency wavelet. And as I say, we'd like to define it with a linear model. But what should be this model? So the first idea that comes to mind is to say, let's go to high order moments because these are very non-Gaussian properties. The problem is that there are much too many and very high variance estimation. Second approach, let's learn. We use a deep net and try to learn them. Good, it does work, but you end up with a very large number of coefficients and you don't really understand what's happening. What I'd like to show is that for these physical fields, we have all the mathematics needed to specify that, at least for stationary ergodic field. So, first, observe one thing. If you take the wavelet coefficients The difficulty is that they are not correlated at different scales. So why is the correlations of different coefficients zero? Because these coefficients have a phase which fluctuates, and because they don't have the same frequency, you can verify the expectation is going to be zero. So if you want to capture these nonlinear dependence, you need to kill the phase. You can do it with a ReLU. More simply here, we're going to do it with a modulus. So essentially, we're going to separate the phase and the amplitude. We're going to do that by looking at the correlation of the modulus of these wavelet coefficient, but also of the phased coefficient with the modulus coefficient. And in order to have a very sparse set of matrices, because these correlations have to be calculated for any translation, one can show that you can compress these matrices by doing a second wavelet transform. So it leads to that kind of architecture. First, you do a first wavelet transform. You apply your nonlinearity. Then you apply your second wavelet transform. And then you renormalize all coefficients, as in the renormalization group approach, and you compute the covariance at each scale. You can view that now as a kind of simple deep network where there is no learning of the weights. All the weights are specified by wavelengths. If you do that, here are the kind of synthesis that you obtain. So these are original images. Their size is about 50,000 pixels. From a single image, we estimate the Gibbs energy, in other words, the parameters, and here there is about 500 such parameters out of these covariance, and then we sample these probability distribution, and you can see now that you are able to restore the geometry of these fields. In other words, the geometry of this field was captured by capturing the scale interaction and the alignment of the phases. Okay, now let's move to more complex problems, and in particular to regression and classification problems. So these problems are very similar in the sense you don't want to compute the probability of X, but the conditional probability of the label Y given X. So the idea is to use the same kind of strategy. So use these scattering network, which consists in first apply a wavelet transform and your nonlinearity, then reapply the wavelet transform and the nonlinearity, and we'll do it only twice here as we did previously. And then all the images, we output them by averaging and subsampling. So you get your output, which correspond to these cascade of wavelet modulus, wavelet modulus. And we'll then do a linear classifier, which amounts to do a linear combination with appropriate weight in order to classify and get an estimation of this log probability. This is a logistic classifier. Good. So we began to study that quite a long time ago, and the first PhD student on that was Johan Bruna, who's now a professor at NYU. And we tried that on relatively simple classification problems. So if you take simple problems like classifying digits or classifying textures, you can essentially do as well with that kind of network than with a deep learning, with errors in these cases of the order of 0.5% because there are not so many samples. The key reason why you can do that is that here you have a representation which almost linearizes small diffeomorphism, and there are interesting math behind that. So when a digit is written with a slightly different style, it appears in the output of your network through a linear transformation of the weight that you can eliminate with your linear classifier, which explains why you can build the appropriate invariants and get the result. Now, if you move to a more complex problem such as ImageNet, which has 1,000 classes, much more complex classes such as mushrooms, different kind of animals, dogs, and so on, then it's much worse than a deep net. You perform an error of about 50%, whereas a ResNet, not even so deep, 18, will do 5 times better. So obviously, learning is needed. And the whole question from there was, okay, what do you need to learn? What are we missing? So let's come back to the architecture. That's the work of 2 PhD students at ENS, Florentin Gut and John Zak. If we take back the architecture, the idea is that each time we build images with wavelet transform, and as I explained in the physical case, what is going to be crucial then is to build the interaction models of which in some sense represent these conditional probabilities. Now here we are going to learn these interaction models. They are going to be given by a 1-1 convolution operator. This means that it's a linear combination of all these coefficients, which is going to be identical at all positions. Then you take your modulus, you normalize, and then you reapply your wavelet transform. You get all your coefficients, and again, you learn the linear combination before again applying your modulus and preserving the coefficients. And each time you can view these linear combinations as projectors also, which are going to reduce dimensionality. You do that at each scale. So in such a network, you don't learn the spatial filters. You don't learn them because essentially you know that Wavelet will do the job to separate scale across orientations and different scale. What you learn is the interaction terms, which will be crucial to capture the conditional probabilities. And then at the end, you do a final linear classifier. So let me finish on that. Here is the network. It's essentially almost standard deep nets. The only thing is, again, you don't learn the spatial filters, but you learn the filters across the channel. I'm going to use exactly the same kind of architecture as standard ResNet, 64, 128, 512 channels. There is no bias in such a network. And then you need to learn these 1-1 convolutional operator, which you are going to do with a standard stochastic gradient descent. Okay, so if you don't learn anything, that means that these linear operators are the identity. You get a standard scattering transform, and the error is about 4 to 5 times worse than ResNet. This is true for ImageNet, but also for smaller images such as CIFAR, which are also about classifying cars, boats, dogs, and so on. Now, if now you learn these operators, which you have this learning scattering, then you get to the level of ResNet with, in fact, fewer layers. So what does that mean? It means that all the information is indeed captured by these interaction filters. So now the mathematics is about understanding them. We know that to go from one layer to the other, you don't need really to learn anything because you are just doing scale separation and potentially angular separation, which you'll do across wavelets. But these are large 1-1 operators, and understanding their properties is now a very, very interesting problem. If you have very simple problems such as synthesis of 5-4 Ising models or relatively simple turbulences, then you can have models. But for problems such as classification of ImageNet and so on, it's now much more complicated. So, in conclusion of all, the first maybe statement will be that we are all looking for a source of regularities which explains why these neural networks are able to circumvent the curse of dimensionality. My claim here is that one very strong source of regularities is the regularity across scale. And this is the core idea of the renormalization group. In fact, it's a way to revisit the renormalization group with different mathematical tools and express all properties of the renormalization group with conditional probabilities in these wavelet bases. Now, you still need to build these models of scale interactions. So what I tried to show here is that these scale interaction models must be nonlinear. They must be nonlinear because you have coefficients which oscillate at different frequencies, so essentially have no correlation. If you put a rectifier or a modulus, you build up correlation, and you can exhibit some form of dependence across these different scale, which I showed on this turbulence example. Now, what I also showed through these last classification result is that it looks like you can indeed learn these interaction filters with standard deep net strategy. So what are they doing? There is some chance that these filters also captures some form of memory, important patterns and so on. But what is the underlying mathematics? This is essentially very open as a question. So I'll be finishing on that. There's two essentially pieces of work with my collaborators, Thierry Marchand, Miyazaki Ozawa, and Giulio Biroli for the statistical physics problem of the renormalization group, and with Florentin Gut and John Zarka on the image classification problem. Thanks very much.
Thank you very much, Stefan. So we are now collecting different questions that have been asked at different platforms. In particular on YouTube and also maybe on Zoom. So yeah, well, there is a question that is actually the same I had, which is, what is the purpose of renormalized variances in the Biroli and other papers? So how come that at every scale you need to ensure variance constant? That and what would happen if it doesn't if you don't do that?
Okay, I have two choices. I can show that with two slides because this is the core of the math, and it's interesting. Maybe I'll do that to try to answer that question, because it's indeed a very interesting problem. So what is the role of this renormalization? To understand that, I'm going to take a very simple example. I'm going to take a Gaussian process. So a Gaussian process has a covariance matrix, and it's given by probability distribution, which is bilinear like that. So it can be viewed as a linear model where the model parameters is in fact the inverse of the covariance, because that's the inverse of the covariance that appears here. So you need to estimate that, and your phi of x are just all the matrix of second order matrix. Now, what is the condition number of this problem? If you look at the Hessian of the log likelihood, it's going to be the covariance. You can show that if the condition number is kappa for the covariance, it's going to be kappa squared. Now, what kind of covariance matrix are we facing? When you deal with something like turbulence, you have a power spectrum. In other words, your covariance, because it's stationary, it's diagonalized in the Fourier basis. And the Fourier coefficient are going to have a power law decay. So what it means is that the ratio between the smallest, if you look at the inverse covariance, the smallest and the largest eigenvalues have a very large ratio. You have a very badly conditioned problem. What can you do? Here we are ending in a very typical problem in harmonic analysis. You have a singular operator whose spectrum increased like omega to a certain power, like the weight in a sub-LF node. What we know is that these kind of operators, you can precondition them in a wavelet basis. How do you do it? Well, instead of looking at the ratio of the eigenvalue from low frequency to high frequency, you split your frequency into dyadic intervals. Now, within each of these dyadic intervals, the ratio of the largest to the smallest eigenvalue is always a constant. So the condition number is going to be of the order of 1. And you bring it to 1 by renormalizing. So what you see here is that the math which are behind that comes from the fact that the wavelet bases are almost diagonalizing the underlying Haitian. And when you are renormalizing the wavelet coefficient, you are essentially bringing all the eigenvalues to 1. So you have a fast convergence. So what I wanted to show through this example is that the mathematics of all these problems are really about controlling these Haitians, making sure for the convergence that these Haitians are well conditioned. And here you end up in very interesting harmonic analysis problem, because that was a lot of, there has been a lot of work in harmonic analysis about understanding how to precondition such singular operators. And in this case, that's a relation. That's why we do the renormalization.
Okay, so it's interesting. So it's based on preconditioning of operators to a certain extent.
Exactly. That's exactly.
Yeah. Okay, so there is another question about capturing memory. That is something that you mentioned at the very end, and that's something that one of the participants would like to understand better.
So the reason why I mentioned that is that we've been looking at this kind of network in very different kind of situations. And you can see that, for example, in audio, it's almost a bit simple. You can see that the weights are sensitive, for example, to the harmonic structures of the audio, at least some of the neurons. And similar experiments, a lot of experiments have been done in on these networks showing that certain neurons are sensitive to certain type of pattern. Now, wavelets are totally generic. They can't do that. So if this information is somewhere, it must be in the interactions of channel. Now, the question is, how can you do that mathematically? And there are interesting ways to think about it. In fact, compressive sensing is one way to think about that, because compressive sensing is a way to store, in some sense, memory through random measurements. So there are avenues of research around this, but I must say at this point, we really don't know how this memory capturing has been done. Okay, so there is another question that is about somehow the this sort of learnable scattering network, where you do have these projectors that come into the game that kind of try to create these connections between channels. The question to you is there any computational advantage that this kind of network can show in the learning phase, let's say, with respect to a totally brutally trained network like other networks like image like the ResNet or something. Yeah. So yeah, that's indeed also a good question. I would love to say yes, and the immediate thought would be to think, well, because you put more prior, in particular on the spatial filters, you should be able to learn with fewer example. However, you are also in competition with very smart ideas that have been used to compress these networks and so on. So we haven't tried to demonstrate much further any practical improvement, because I've been observing that on this race of having better practical algorithm, we are losing. So the goal here is rather to disentangle the different phenomena. Now we have much simpler operators. We try to understand that. it doesn't mean that at one point, if we understand these operators, we won't be then in a good situation to have better performance than by putting more prior information. But as long as we don't understand these operators, we still are learning a very large amount of coefficients. And the advantage towards ResNet is not so clear.
Okay, it's very clear. So basically, you are trying to single out the different fundamental mechanisms that are happening in this kind of image processing networks, and to try to disentangle the different effects, and rather than building up a sort of more competitive at the competition level. So you're really trying to disentangle different parts of
the goal is really to understand the math, the robustness, and so on, so that at one point, indeed, we can improve. But let's face it, I mean, if you look at the state of the art of DeepNet, it's GPT-3, Lambda, and so on, which are learning over the whole internet and so on. It's extremely difficult to do both. Be better algorithmically, so in the scarce data regime, we can, in the physical applications that I showed, because in the physical application that I showed, we don't learn at all these operators. So we can learn a model from a single observation. But the day we begin to introduce these operators, as long as we are not able to structure them, we don't have a real game. So the key question is now to be able to structure these operators.
Okay, so other questions coming from the Zoom participants, in case you may want to come forward, even speaking. And okay, so maybe another more general question is, it's about how fundamental is, in your view, the effort of mathematicians to work for an explanation of how deep networks do work, and how much instead somehow statistical based advances, say, based on beating benchmarks, could be acceptable as a reliable process in understanding machine learning at this scale.
Okay, so it's obviously a very important question. So I think it's not an opposition between both, the way I view it. I consider that nowadays it is an absolutely fundamental scientific question, because you can learn physics, quantum chemistry, turbulence of physics, meteorology with such systems. You can learn languages. So it's an incredible mystery. It's about understanding the mathematics of high dimension. For me, this is really the topic which is here. And it's a considerable challenge. It's opening huge questions. It requires to go well beyond standard. Okay, one observation is that we are, from a mathematical point of view, we are naturally in the world of probabilities and statistics. High dimension means that you cannot anymore estimate values at points. You need somewhere to have concentration phenomena in order to be able to get measurements, which is why you end up doing statistics or probabilities. But we are now going well beyond Gaussian processes, toy models such as Ising and so on. So for me, it's a lot of air for mathematics. The reason why it's also obviously very important for applications are all the questions of robustness, control, understanding whether there are bias, and mastering that kind of technology. But on the other hand, you are also right that you can take a totally empirical statistical approach. And this empirical statistical approach does work also very well in terms of applications. If you have, the whole problem is the data bias. You can have a system, if you test it on, as you know, on data which are biased, then you have issues about generalization. But if you have sufficiently well gathered data, statistical tests can be sufficient to prove robustness. If you have cars that goes on the road for many weeks with no accidents whatsoever, at one point you'll consider that the system is robust, at least more robust than a standard driver. So I don't see the two in opposition. However, these kind of statistical tests can be difficult because you have rare events, corner cases that are important, like the little kid which is running after the ball, which is crossing the street. And understanding better the structure of the mass can help isolate such structure case. So my answer is, from a mathematical point of view, from a scientific point of view, even from a philosophical point of view about the notion of what is knowledge, these are crucial questions. And mathematics is at the center. Yes, it's very important for applications, but let's face it, mathematics is very, very far behind. So I do think that it's needed to have a good mathematical understanding, but it will take time before this mathematical understanding improves applications. Right now, applications are moving through essentially experimental result, but no, maybe I go too far, because, for example, if you look in generative models, there has been very beautiful results recently on score diffusion algorithms, which are essentially based on inverting stochastic differential equation. So the core idea comes from mathematics, but the problem is still totally open because there is a slight details in these algorithms, is that you need to estimate these so-called score function, which is a high dimensional object. And there you go back to your deep network and you don't understand. So mathematics here helps to give the other broad framework, but the reason why it works or doesn't work is still, why can we approximate high dimensional functions? So that would be my answer. No position between these two approaches, but I think it's an amazing opportunity for young researchers now.
I have one more question that has a bit of flavor of being technical, but it doesn't. So often, and you also said something of the kind, that deep learning is able to beat the curse of dimensionality somehow, or it seems to beat the curse of dimensionality. On the other hand, the most spectacular results of deep learning occurs when you really train the model and you try to identify the parameters over a number of data that is really, really, really large. And also the cost of processing this data and the learning phase is not really counted in terms of floating point operations, I would say. So is it really true that somehow somehow neural networks do beat the curse of dimensionality? We know that for certain kind of functions, you can approximate them by using neural networks without having to incur in the curse of dimensionality, but the identification of the network may require still a very large amount of data. And so the question remains to a certain extent. What do you think about that?
So first, you're absolutely right that as the amount of data is increasing, we see a jump in qualitative performance of these networks. So amount of data is crucial, but we're still, this huge amount of data is very, very small compared to the dimension. Curse of dimensionality means that if you have no very strong regularity property, the number of data grows exponentially with the dimension. So that means that even in dimension 100, you go well beyond the number of atoms of the universe in terms of number of data to approximate a function that is Lipschitz. So you need something which is much stronger. So yes, the curse of dimensionality is still very strongly there in all these problems, despite the fact that you have billions of or millions of examples. But it doesn't mean that you can do it with obviously a small amount of data. So this is the difficulty. These are not low-dimensional models. And the difficulty also comes from the fact that the models are both in the distribution of the data and in the function of the data. So it's both in X and Fx, and the both are mixed, and it is this mixture where there is this global regularity which emerges. So yes, I do strongly believe that there is, well, it's not a belief there. It's mathematically clear that they are beating the curse of dimensionality in the sense that you can't approximate Lipschitz or Sobolev functions even with high degrees of regularity with arbitrary such functions with such networks. So somewhere there are much stronger structures.
Thank you. So there is one question coming from a Zoom participant, in particular Volker Trespe. Please, Volker.
Okay, can you hear me?
Yeah.
Yes.
Okay, great. Yeah, fantastic talk. I'm really impressed that you're really taking on the big challenges here. Two aspects people are always discussing in the special properties of deep learning. One is that the input data is really on a low-dimensional manifold. And the second comment is always that the model or the nature produces compositional functions. Do you have comments on these two aspects?
Yes, I have comments. Thanks for asking the question. I have strong comments, in fact. First, data is in low-dimensional manifold. This is wrong. This is just plain wrong. If you take the data that I showed, turbulence, if you take this cosmological image, if you take any natural image, you have textures. Textures are not in low dimension. They are in high, they live in high dimension, which doesn't mean that there is not structures that lives in low dimensions, such as some shapes and so on. But the whole problem is that it's wrong to say that the data is in low dimension, unless you say that low is 100,000 or 10,000 or several thousand. But a dimension of 1,000 is a very high dimensional space. It's what I mean by not low dimension is that it's not in dimension 5 or 10. So if it's not in that, once you're in dimension 100, you already suffer the curse of dimensionality in a very strong way. So it's not true. On the other hand, it's not because you are in high dimension that you cannot build low dimensional models. For example, Gaussian white noise is everywhere in the space, but you can still define a simple model with one parameter, which is the variance, and given that the covariance is identity. So there is two different things, which is ability to build models with a low dimensional model and the fact that the data itself is in low dimension. The data is not in low dimension, but you may be able to build, let's say, relatively low dimensional models of the data, which is, it's not the same because, again, the manifold corresponding to Gaussian white noise is the whole sphere in high dimension. The second point, sorry, that you mentioned was?
Compositionality.
Yeah, composition. Yes, the problem of this property is that it's very hard to specify, because what are you composing? I have a tendency to agree that there is this compositional element. In fact, if you look in the renormalization group ideas, you go from one scale to the other with these conditional probabilities, which defines operator from one scale to the other. And when you go like that, you are composing these conditional probabilities. So it's a compositional model. So yes, I have a tendency to agree that compositional models are very key. But once you've said that, and this observation, as you said very well, was done very early on when people began to study neural net in the 70s. There is a big jump towards to go to having a model that can that has no curse of dimensionality, because you need to specify these composition. But as I said, there I would have I would agree that it's a very important property.
Okay, maybe I can follow up on the first issue. So if you don't think the manifold is the key to understand deep learning, how do you explain, or what is your explanation for the catastrophic failure in some testing results and these adversarial examples and so on? I mean, the manifold sort of interpretation is sort of nice because you can assume, like, on the manifold, the model is very good, but if you go away from the manifold, you don't know what's happening. So if you don't believe manifold is the key to understanding deep learning, do you have a good explanation for this catastrophic generalization sometimes people are observing?
Okay, so but I would like to say it's not a belief. I think it's an observation. The images which I showed are natural images. They are not in low dimension. It's not a belief. It's I mean, there are, even in the case of 5-4, for example, these are high dimensional. If the turbulence are high dimensional objects, it would be known in physics if turbulence was low dimensional. So textures are not low. Now, again, it doesn't mean that you cannot build low dimensional models, but it's not on a low dimensional manifold. And I don't think that this is of the order of the belief. The word manifold is very ambiguous because mathematically, when you speak of a manifold, usually you think of a Riemannian structure. You have a different structure, differential structure. And to do that, you need to have access to neighborhood. When you're in high dimension, of course, you can say that the sphere of a dimensional D space is a manifold, but you cannot have any local access. So if the word manifold means a surface of any dimension, yeah, but low dimension, that I think is beyond belief. It's a fact that data is usually not at least not always, or very far from as soon as there is texture. If you think, for example, of voice, when you make an unvoiced sound, these are random processes which are almost Gaussian and which are high dimensional. So what about catastrophic behavior? Catastrophic behavior are about instabilities in the estimation of the coefficients. So they can come in many different flavors. The fact that the underlying operators that you are having are unstable. I gave the very simple example of the Gaussian process where the Hessians are unstable. Means that it's very hard in the nonlinear case to control all these instabilities. So I don't have mathematical models indeed to explain these instabilities, but I can see that there can be a model based on low dimensional manifold, but I don't see why this should be a necessary condition.
Mm-hmm. Okay, thanks.
Okay, so thanks a lot for being with us. and for taking our questions and responding so graciously to them.
Well, thank you very much. It was very interesting to have these discussions, and I hope to have more exchange, but it's thank you again.
Yeah. So now somehow we can move forward to the moment where you will be maybe meeting with some students that will stay with us and having a moment with you, having the opportunity of talking about the concepts that you presented today, or more in general about the role of, say, mathematics in this business. So I thank all the participants for coming also to this event, and there will be further opportunities and talks coming in this colloquium series. And yeah, thanks a lot for everybody for coming. And Stéphane, if you want to stay with us,
Okay,
yeah, we can meet with the students.